Good day, good day. Welcome to Africa Teen Gig Online School. If you are just joined us in, this is the Physical Sciences Grade 11 class. Who I hope you guys are having a great day today, as we keep moving on with our syllabus as it's prescribed on our CAPS syllabus. I just want to remind you all that we are going to be doing our work. We've been actually doing our work following up on the Oxford Successful Textbook. So if you have the Oxford Successful Textbook, that is a plus. But if you don't, you can still get it. It's absolutely free. You can get it on Snaplified. It's an application that you can use to get all your textbook, not just for physical sciences, but for all other subjects and different types of books like Siavula, um, what's the other one, Master, Study Master, and all of that. So if you guys want to upgrade yourselves and get some more input from other different subjects and textbooks, you guys can go on Snaplified and register yourself. These books are free for the whole year because of the COVID-19. My name is Nonkulilego Madondo, and I am your teacher for physical sciences grade 11. You guys can get me on my social media, which is LinkedIn as Trio Madondo. And whenever outside of this class, you guys can just send me DMs on LinkedIn and tell me what problems you guys are encountering. Another thing that I wanted to let you guys know, once we're done with this module 5, because now we are on chapter 5, um, you guys can make up all these questions, and you guys can also send them to me because we will be doing revision, I think, on Friday. Yes, I'm not sure yet, but I'll let you know. We will probably be doing revision on all the units that we've done uh, from chapter 5, which starts from stoichiometrics, calculations, um, volume masses and moles and all of that. So we will be doing revision. So you guys, please stay in tune and make sure that you do all your homework. Well, once again, as you know, every class I give you guys homework, and I asked you guys to do homework for. Let me just open the textbook for the work that we did yesterday, which was limiting reagent. I really enjoyed limiting reagent, and I hope that you guys did too, and you guys are understanding it a bit more. Um, I'm just trying to open the textbook just to see the questions, and I hope that you guys were able to do number 2. I asked you guys to do number 2, and I said that if you do have the time and energy, um, you can also do number 3. I have done it and we'll go through it. You know what I like about these questions here? It's because they touch base, especially on things that were not really in depthly explained in this chapter. Because there is some other things that they asked for, like the masses of the excess chemical. Those things were not really explained, but they are there in these problems. So if we do these problems, we'll definitely be tackling two birds with one stone. Okay, my computer is a bit slow as usual. I'm sorry about that, but I'm just trying to get to the question that we are working with today, and that was given to you guys as homework. Yes, here we are. Okay, we already did number one. If you guys remember yesterday, we did number 1, and I hope that gave you guys a clearer perspective on how to get to your limiting reagent. Because in this unit, basically, they were trying to we were trying to explain how the limiting reagent works and what it means and why is it used in a chemical equation, or better yet, why do we look for it in a chemical equation? Okay, so we did number 1. So on number 2, it says at high temperatures, sulfur combines with iron to form brown black iron sulfide. Okay, there we have it. It's Fe plus S will give you FeS. Well, this is a standard, easy normal equation. I think this was done using the volumetric flask. I think this is a standard um, standard formula basically. Yes. So they say a reaction takes place in a mixture of 7.62 gram of iron and 8.67 gram of um, S. Okay. So what are they looking for? In this case, it says on number one, determine the limiting reagent and the reactant in excess. Okay. On number two, it says calculate the mass of FeS that forms. Number three, it says calculate the amount of excess reactant that is left over once the reactant is complete. Okay. So now what I'm going to do with you guys, I'm just going to quickly go to the problem. Okay. To the homework. Okay. So you can see here on number two, just take a look at it. And I hope that you guys did the very same thing that I did. And okay, so when you check for the mole, what we first do, as usual, we need to find the number of moles. That's a standard that we do every time. We look for the number of moles of each. Okay, they've given us the masses for both, so we need to find both number of moles. And why are we doing this? We need to find the limiting reagent. Once you're given two masses, it means that one of them is a limiting reagent and the other is in excess. They can't both be limiting agents. And number two, what we need to understand about this is that the limiting reagent is important because that is what we're going to use to calculate the amount of the product. I hope you guys are understanding what I'm explaining here. You need the limiting reagent to calculate the amount of the product. You cannot use any other. And you know, it's not easy for you to just assume that which one of the two is a limiting reagent. So that's why in this part, we need to calculate and find out what is the limiting reagent. Okay. So this is the mass of Fe, and this is the molar mass of Fe, and this is the molar mass of S. Okay. So what does this mean of sulfur? So we checked for the number of moles of each, and we said M divided by molar mass, which is the masses, and for N we got 0.1364 mole of iron, and with this one it's 0.2704 mole of S. Why? Why do you write mole of Fe or mole of S? It's very important, guys, because sometimes you're given a lot of data, so it becomes really hard for you to understand, okay, which one is which. So it's always best for you guys to write that this is a mole of Fe, this is a mole of S, okay? And then number two, that was the first step, calculating the number of moles. And number two, now we're going to look for the ratio. What is our ratio in this case? Our ratio means that is our baseline to know that if 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 our ratio is greater than if the ratio of the number of moles that we're going to find is greater than this baseline that we're using here, it means that for example, Fe will be the limiting reagent. But if it's more, then S becomes the limiting reagent. So we look for it like this. We say Fe divided by Ns, which is obviously we're taking the numbers in front of the element and the compound, okay? So with Fe, there's no number, so we assume it's a 1. And for Ns, there's also no number, so we also assume it's a 1. And that will be equal to 1, okay? After that, what do we do? After that, we take these two, and basically we look for, we divide them amongst each other again. So basically we're looking for the ratio now, okay? So what are we going to know? What we know is that if, since this is our baseline number, this number 1 that we already calculated, Sometimes you get that S will be 4, then it will be 1 over 4, and then that will be the baseline. So this one, if what we're going to get from the ratio when we calculate the number of moles of these two, if it's going to be less than 1, then the Fe is going to be our limiting reagent. But if it becomes more than 1, then our Ns will be the limiting reagent. Okay, so now we calculate it. We take 0.1364 and we divide it by 0.2704. Okay, and what will that give us? That will give us 0.5044. So what does this mean? This is 0.5 and this is 1. So which means that this is less than 1. So if it's less than 1, it means that our Fe is the limiting reagent. Do you guys understand? If you don't understand, just drop me a chat quickly and I'll go through it again, because this part is very important, because that's how you find your limiting reagent. And if you can't do it, then your answers are likely going to be wrong when you get to this section. Okay, so you see, because 1 is greater than this ratio that we got here, Fe is a limiting reagent, and because you only have 2 elements in this equation, then ultimately S will be the reactant in excess. Are you guys with me? Well, I hope that you guys are with me. Okay, then we move on. Then now, what are we looking for? What we are looking for is the number of moles of this one here. Okay, let me just check if everybody is together. Good day, Ahmed. Can you please explain it all again? Okay, I'm going to start over. Okay, we've got steps now. What is a limiting reagent? A limiting reagent is the substance that is limited in the equation. So what it means is that, for example, if Fe is a limiting reagent, it means that once Fe is depleted in this reaction, then this one will be formed and it will not continue to react any longer. Okay, so that's our limiting reagent. So why do we need why do we need to calculate the limiting reagent? We need to calculate it because um, the limiting reagent comes from the maximum used of our product comes from the maximum use of our limited reagent. So we cannot use the one that's in excess, because if this one is in excess, then it's more than enough. Some of it is going to be left over. So we can't use it to calculate what we have in our product. So we need to find the limiting reagent. So what do? We don't know what the limiting reagent is between the two. Why? Because they've given us both masses, and that's all the information that they've given us. So we are going to have to find the limiting reagent on our own. So what do? We go to the molar mass. We look for the molar mass of Fe. These molar masses, you can find them on your periodic table. Everybody should have a periodic table, especially when you're working with chemistry. Okay, on your periodic table, you will get the molar mass of Fe. And then once you get it, then now you can calculate the number of moles, because remember, that's our first step, calculating the number of moles. Whatever you get in all the calculations in our chemistry that we've done so far, the first step that you do is convert, whether it's a mass or whatever particle is given, you convert it to the number of moles. So here we are. Now we've converted it to our number of moles, and then we also do the same for sulfur. We get the molar mass on the periodic table, and then we calculate the molar mass, and that will give us 0.2704 mole of S. That's why I tell you guys it's very important that you write mole of what, because like here you've got 2. Maybe when you go on later on in the problems, you might confuse them if you haven't specified what each one was calculated for. Okay, and then after that we go to our ratio. We need this ratio here. It's the baseline that we're going to use to calculate, to know whether our which of these elements is our limiting reagent. Okay, how are we going to find that? For example, we're going to take NFE, which is the first one here, and we're going to divide that by NS, which is this one right here. Okay. And which numbers are we taking there? We're taking the numbers in front of our elements. You see, why did we take a 1? Because there's only one FE, and here there's only one S, because there is no number. If there was 3 here, we were going to write 3 on NS, but no, it's a 1, so we write 1. So this is our baseline. Okay. So what do we know about the baseline? The baseline, the rule says that if, for example, you calculate the ratio of number of moles of Fe and you divide it by the number of moles of S. If you divide these two and the number is less than this number that you have here, which is 1 in our case, then our limiting reagent will be Fe. But if you say NFE and you divide it by NS and you get a number that is greater than 1, then our limiting reagent will be the NS. I hope you guys are understanding what I just explained. I hope it makes more sense. So that's how we get it. If this is our baseline here, if the NF divided by NS is less than 1, then our limiting reagent will be Fe. But if the NFE divided by NS gives you a number that's greater than this number here, then our limiting reagent will be the S. I hope that you guys are together with me. Okay, can I continue? If you're still confused, drop a chat again and I'll express wherever you're having problems. Okay, so let's continue. Now that we know what our limiting reagent is, because here we divided the two and it was 0.5. So what did it give us? It gave us an amount that is less than 1. So what does that mean? It means that our limiting reagent is Fe. Okay. Let me just check somebody who's also having a problem. Okay, hi Lerato. The link to this lesson for if you like to review on YouTube. Okay. Thank you guys. I thought that was for me. So I'm glad that Lerato seems to be getting it because she's talking about something else. So do you guys get it? Okay. So now we've got our limiting reagent and we have our reactant in excess. How do we know S is the reactant in excess? We know this because there's only two elements. One will be a limiting reagent and the other one will be in excess. Okay. So what we're going to do now is that now we can calculate the product. Okay. Like I said to you guys, the product, we always use the limiting reagent to find the product. Okay. So what are we going to do? We're going to go back to our ratios. So we're going to say NFE divided by ratio FE. Remember what I said about the ratios? I said with the ratios, once again, it's the number in front of the element or compound, okay? And then N is the number of moles, okay? So we're going to take the limiting reagent and equate it to what is unknown, which is the FES, okay? So with the number of moles for Fe is going to be 0.1364, which is the one that we got here. You see, guys, you see why I say it's important to write mole of Fe, because now you could have wondered, okay, which one is which that I'm looking for, but it's easy to find if you write mole of Fe, okay? And then divided by 1, because there everything is a 1, so we don't have any funny number or ratio numbers that we have in front of anything in this equation. Okay, so we say that is equals to NFES, which is the unknown, divided by 1 because the ratio is 1, and our NFES will be equals to 0.1364 mole of FES. I hope that you guys understand how we got to this. And if you don't, please guys, don't hesitate just let me know and I'll go back and explain what you guys do not understand. Okay, so this is our answer. So on number 2, let's quickly go on the second question and just find out what they say there. Okay, so we managed to find our limiting reagent and reactant in excess, and we found the mass of FeS that is formed. Okay, so the product, guys, remember, you always use the limiting reagent to find the mass of the product. Okay, so on number 2.3, they say calculate the amount of excess reactant that is left over once the reaction is complete. Okay, do you get what that means? So it means that um, you're going to have a reaction, you're going to have your limiting reagent, and you're going to have your reactant in excess. But you're not going to use all the reactant in excess because some of it is going to be left behind because the limiting reagent is limited. Once the limiting reagent is used up, then you've got excess reactant that is left behind. So that is what they are looking for. That, okay, once the reaction takes place between Fe and S, there's still some S left. So what is that amount of S that is left behind? Okay, so let's go and check it out. Okay, so what do we know about looking the um for the reaction in excess? Okay, number one, we need to find we need when we look for the reaction in excess, what we do, we equate the reactants on their own. So now we leave the product out of it. We're going to make a ratio of the iron and equal it to the sulfur. So you take your two reactions and you equate them as ratios to each other, as you can see here. Let me just make the screen a bit smaller. Okay. If you check here, when you look for the amount in excess, you ignore this part now, okay? Because you've already used this and we use the Fe to find that. So now what we do, we focus on this one because this is where the reaction is taking place. So it means between these two, we will know what happens and how much is left behind. So we're going to equate them on each other, against each other, and find the unknown, okay? So going down, yes. So it will be that ratio, and our NS in this case is what we are looking for. Okay. So we're going to take the ratio. This is going to be 1, 1, obviously. And then NFE, we already have it, is 0.1364. Okay. Why? Because if this both is equal to a 1, so there's nothing to cross multiply anymore. NS is equals to NFE. Okay. And then after that, we look for the mass. The mass of sulfur is going to be 0.14. I just made it 0.14 because with the book, they always with the mass, they always take it to 2 decimal places for it to get an accurate answer like the one that's in the book. So it's going to be 0.14 times 32.07. What is 32.07? This is the molar mass. This is what you get from your periodic table. So this equation is M is equals to N times capital letter M, which is the molar mass. And this is what we're going to get. So which means 4.49 gram of sulfur is what is going to be left behind. Guys, are you guys understanding? Are you guys with me? Because if you're not, this is your time to speak up before I move on to the next problem. Okay? I hope you guys understand that. It looks very difficult when you look at it, but it's quite simple to find the amount in excess. Okay? So this was the amount in excess. Okay? So now we're going to move on to the next question. Okay. The next question says, this is number 3. It says acrylonic trial. Okay, guys, this is physics. It's not my mother tongue. Acrylonitrile, which is C3H3N, is the starting material for the production of a type of synthetic fiber. Okay, it can be made from propylene C3H6 by reaction with nitric oxide, which is NO, as followed. Okay, so here they've given us a balanced equation. How do we know it's balanced? Because we've got all these big numbers on the side, which show that they try to balance out the equation. Okay, so in the reaction, 2.16 gram of C3H6 and 21.6 gram of NO are added to the reaction container. Okay, calculate the volume of N2 gas, which is a nitrogen gas, that is produced at STP. Okay, so we're going back to one of our old formulas and infusing them in one of these formulas. Okay, so we know what the first step to do. The first step, we get the number of moles. The second step, we get the baseline of calculating the limiting reagent. Number 3, calculating the limiting reagent. Number 4, using the limiting reagent to find the product. And after the product, we'll take it from there. So those are the first 3 steps that you know, whatever you do in this kind of problems, those are the ones you're going to have to start with. Okay? So let's go to the problem. Okay, so I'll okay, I don't need to because it's only one question. Okay, so this is our balanced equation and this is the given. It's always good to write what's given so that you can not forget to know what you already have, because sometimes you find people calculating things that are already given because it gets really hectic in the exam room. You can just start calculating something that is given, so it's always best to see what is given. Okay, so now here we go. We find the molar mass of C3H6, and this is what we get. And then we go to the number of moles and we find our number of moles. As you've seen, I've written here, is 0.5133 mole of C3H6. Okay, and then after that we find the molar mass of NO, which is what we get there, and then we find the number of moles for that as well. Okay, so because we don't know, remember, once you see a problem, you don't know what your limiting reagent is. It's what you're going to find. So it's between C3H6 and NO. One of them is our limiting reagent. Okay, so we move on. Now we go and find, remember I mentioned before, our baseline, which is a ratio. Okay, for us to know if our ratio is greater, if what we're going to find when you look for the division of the ends is greater than the ratio that we get here, then our limiting reagent will be NO. But if it's less than this, then our limiting reagent will be C3H6. Okay, so where do I get 4 and 6? 4 is the number here. Remember, I told you it's always the number in front of your compound, okay, or element. So in this case, it's a 4, and for NO, it's a 6. So that's where all the 4 and the 6 comes from. Don't forget that. If it's not given, you assume it's a 1, okay? So here we have it. We've got 4 and we have 6, and this is what we get. So now what do we do after that? Now we actually take the actual number of moles calculated and we divide them both by each other. So it's going to be NC3H6 over NO. It's going to be 0.5133 divided by 0.7199. Where do I get these ones? It's these ones that we calculated here, the number of moles, 0.5133 and 0.7199. Okay, and then the number that we get here is 0.713. So 0.713 is greater than the baseline that we calculated here. So what does that mean? If it's greater than this one, it means our limiting reagent is NO, the one at the bottom. But if it was less, it would have been C3H6. Okay, so which means in this case, NO is our limiting reagent. Okay, so now that we have our limiting reagent, now we can go and find the product. Okay, because you need the limiting reagent to find the product. I hope everybody is still in line with me. Okay, so it's going to be NO divided by ratio NO, which is the ratio. Don't forget, guys, it's the number in front of your compound or element. Okay, and you equal that to the N of the unknown. We're looking for the number of moles of N2, okay, the nitrogen gas. And we divide that by the ratio of N2. And let's just see for N2 there's no number in front of it. So it's the ratio for N2 is going to be a 1, okay? And then yes, we're going to cross multiply them both, but we don't have to, because if N2 is equals to 1, then N2 will be equals to NO divided by ratio of NO. And this will give us 0.11999 mole of nitrogen gas, okay? Now that we have a number of moles, we can go straight to looking for the volume at STP. The volume at STP is always 22.4 times the number of moles of what you're looking for. And this is the answer that we get, which is 2.69 dm cubed. I hope that everybody has got that right. I hope that you did try it and you got the answers exactly like I did, because understanding is the main theory here that we are looking for. It's all about understanding. So if you guys understand, then the work becomes easier for all of us. So I hope that you all understand what is going on here. So now we're going back to a bit of theory, because we're going to be talking to the next unit. I'm reminding you guys that now we are on unit 8. Yes, which is examples of gaseous reactions. Why are we doing this? Because it's in your syllabus. These are things that you will get in your exam, so we have to go through it. So we're going to be doing some examples of gaseous reactions today. I am Nonkulego Matondo, and this is unit 8. Okay, so what are we going to do today? We're going to do the chemistry of ammonium nitrate explosives, and we're going to do the chemistry of airbags. I know this is a bit of theory, but there will be some calculations that we see that's going to show that how these ammonium nitrate explosive occur and the chemical equations of the airbags. So I hope that you guys will all understand. Okay, so let's start with the chemistry of ammonium nitrate, and that is our compound, how it looks, our unit. This is how it looks, the formula. Okay, explosive. Okay, so what do we know about this? Where are explosives used, and why is there a chemistry for ammonium nitrate? Ammonium nitrate is explosives that are used to break rock. This is usually done in mines because they can't use their hands to break some of the rock. So what do? They use explosives, and in this case they use ammonium nitrate. Okay, ammonium nitrate fuel oil is explosively used to break rock. Okay, places with such explosives need to have signs, and they're very dangerous places. That's why mines, there's a long distance before you actually get to the actual mine. So that's why they have such things. Okay, explosion is exothermic reaction, meaning that the energy is released through light or heat. What does that mean? It means we're going to have the reactants that's going to give us a product and energy. So you can just think of an explosive. Okay, you've got your explosive, it gets lit up and it explodes. That explosion is light. That explosion is heat. So that's what it means when it says explosion is an exothermic reaction. Okay. And how do we find our ammonium nitrate? This is our ammonium nitrate. So how is it made? It's made through ammonia and nitric acid. Okay, so this is the chemical formula and how it looks like. Okay, so we also have a gaseous reaction. Our gaseous reaction in nitrate explosive. So which means that When it explodes, you have your nitrate there, and you add it with carbon, and this will give you carbon dioxide plus nitrogen gas plus H2O. So this is a whole explosion, and what happens as a result. So this is a gaseous reaction that you will get. Okay, I'm going to go to a problem that we're going to do just now, just to practice what we're doing. Okay, let's go to the textbook. Mm. Guys, for those that have just joined in, you can get your textbook from Snaplified, Oxford Successful Textbook. That's the one that we're using here because every textbook has a different way on how they place their units and topics. So we prefer to use one as a standard to find, to have a pattern on how we do our work. Okay. So this is the Oxford Successful Textbook. Okay. So we're doing gaseous reactions. Um, I hope that my PC is not going to fail me now. Okay. The chemistry of ammonium nitrate explosive. This is exactly what I was telling you guys about. So this is an exothermic reaction because there's light, there's fire, there's heat that's exploded out. So that's what it means. Okay. A typical reaction is this, like the one that I've showed you guys on the slide. As the reaction takes place, the gases that form move rapidly outwards to fill up the surrounding area. This pushes the particle of the surrounding material apart into small pieces. Okay, there's an example that I want us to do now that's also found in the textbook. Yeah, here we are. Okay, they say consider the chemical reaction, which is the one that's given there. If 10 kg of heptadecane reacts, calculate the volume of carbon dioxide liberated at STP. That's the first one. Number two, the number of nitrogen gas molecules that are produced. Okay. So, what do we know about every equation that we start with? Whatever is given, we convert it to moles. Okay. And so here they've given us something in kg, but we know that whenever we get mass on our chemistry, we use grams. So the first thing that we do, we convert our 10 kg to grams. So it's going to be 10 divided by 1,000 times by 1,000. Yes, times by 1,000, sorry. And that will be 10,000 gram. Okay. So please give me a shout if you're getting confused while I'm doing these steps. Okay, convert all masses to moles. That's the first step. Every problem that we have, we always have to first convert the masses to moles. Okay, so it's going to be m divided by m. And don't forget, with the molar mass, the one underneath, you're going to say 6C, which is the carbon, times 17. You're going to put it in the bracket, and you're going to say plus, open bracket, H times 36, and then you close bracket. Between these two, you're going to add them, but whatever you have as a subnumeral, you're going to multiply with the element right in front of it. Okay, so that's why we get 240 over 36, and this is our molar mass. Okay, and therefore we get 41.6 mole. Okay, you can write it mole of C17H36. Okay, why are we using C17H36? Because there's something that was given from it. You always take what is given. You don't take something that's not given to look for. You use what is given first. Okay, and from there, we're going to go back and do our ratios. Remember our ratios, it's going to be N of CH36, H36 divided by the ratio of H17, C17H36. And in this case, the ratio will be a 1 because on CH, C17H36, there is no number here. So that's why our ratio 1 is equals to 1 over there. And then for carbon dioxide, which is what they are looking for, they're looking for the volume of carbon dioxide. We've got 17. So our ratio 2 will be 17. So you just take these two, you're going to say N1 over ratio 1 is equals to N2 over ratio 2. And what are you going to get? Our unknown is the N2 in this case. So you're going to cross multiply these two. It's going to be 1 times N of carbon dioxide times N times 17. So this is going to be equals to 41.6 times 17. And what will that give us? Our number of moles will be 702.2. Are you guys understanding how I got that? If you don't, let me know, okay? And then, because we're going to look for the number of nitrogen gas, we look for the nitrogen gas molar mass, number of moles as well. We're going to do the same thing. We're going to say N1 divided by ratio 1, which is this one that's given here, is equals to N2 divided by ratio 2, which is this 52. And then we're going to cross multiply. You're going to multiply this with 52, and you're going to multiply this with 1. So N2 is going to be equals to 41.6 times by 52. And this is the answer that we get. So now we've got the moles of the things that we're going to look for, okay? So when it comes to carbon dioxide, they want the volume at STP. So now that we have the number of moles of carbon dioxide, we can just plot it into the equation, and Vm, we already have the volume at STP, which is 22.4. So you're going to take this answer times by 22.4, and this is the answer that you're going to get, okay? After that, you're going to do the same with the nitrogen gas, okay? The number of particles, they're looking for the number of N2 gas molecules that are produced. So in that case, number of particles is the N Avogadro. Remember in the beginning of the unit, we worked with Avogadro. So with the Avogadro, it's 6.02 times 10 to the power of 23. And we times that by the number of moles. And this is going to be the molecules of nitrogen gas, okay? I hope that everybody understood that, okay? I think tomorrow, when we start our things, we'll quickly finish off with the airbags, because I still think there's the airbags that we need to do, but it's going to need some time, okay? But let me just go through it quickly. We only have 3 minutes left, so I need to rush, okay? Okay, so the chemistry of airbags. When there is a collision, Na3, NaN3 is, okay. Oh, okay, I don't know what's happening with my screen. But guys, tomorrow's homework that I want to give you guys, because we already ran out of time, and we can just check something out with regards to the NaH gas. Like, for example, can we do number 3 and number 4? Okay, let's do number 3 and number 4, and then we'll work on them tomorrow. And I think tomorrow we will continue and finish off the chemistry of airbags, because it's also quite interesting, and it's things that you guys need to know, and we're going to do it tomorrow. But nonetheless, for now, we are done, guys. Thank you guys so much for being the best guest ever, and don't hesitate. If you have a problem, if you get stuck, just let me know. I'm Nonkululeko Madondo. I am your teacher for this class, grade 11, and I hope that you guys understand every problem that we encountered today. And please, guys, continue doing your homework in order for you to learn, because in physics, math, same thing. It's all about practice, practice, practice. You learn through practice. So the more you practice is the more things get inclined in your mind, and you get to understand it more. So let's do number 3 and 4 for tomorrow, and then we'll work it out tomorrow, and then finish off the chemistry of airbags. Thank you guys so much for a beautiful lesson and have a good day.